Hello and welcome to the start of our review of the senior mock paper. First things first, if you have not yet tried the paper, the link is in the description below and you can feel free to pause this video and give it a try. Right? The paper was released slightly over a week ago. Now, I'm not going to talk about the cutoffs and the difficult and easy problems just yet. Similar to junior, I will wait until the end of going through all the questions to make more general comments. I'll just make some small comments first, which is that for senior, and certainly for this paper, 2.5 hours, not a lot of time. Secondly, 2.5 hours is also pretty tiring for a senior paper where you have to do a lot of work. So I would encourage you, apart from this mock paper, if you have not yet done a lot of the previous SMO papers, try them. If it's the last few years, of course, you can watch my videos. If it is older than that, you can always find the SMO book, read the solutions, but get used to the 2.5 hour time frame. Another thing which I would say is that for senior, there's a lot of content. If you know that you don't know some stuff, let's say you know that you forgot the identities for trigonometry, for logarithms, for polynomials, for surds, for indices, etc., do please go and take a look at them, or even learn a few more if, let's say, you realize that, oh, I've never seen that thing before. Okay, because in some sense, the scary part is when you don't know what is going to be tested. And for senior, at least 10 questions or so are going to be pretty directly correlated to your knowledge. So if you know them, you can get those 10 questions. If you don't know them, you can't get those 10. And this is a bit different from junior, which has a bit less content, but quite a lot of problem solving intuition that is perhaps less formula based. Now, I've entitled this section, of course, Know Your Identities, because in part 1 of our review, we will go through the multiple choice and a couple more problems, all of which have something to do with our algebraic identities. You have to just know them, but not memorize them all blindly because they're too much. Know which ones you need to know. So for example, for trigonometry, you have to know that cosine alpha minus beta is cos alpha cos beta plus sine alpha sine beta. You have to know that there's no way around it. You should also know that from tangent, you are able to get sine and cosine, especially when you know the quadrants, right? This is the second and this is the third quadrant. You should know that the quadrants will determine the sign, but you don't have to memorize the sign. You just need to actually know your unit circle and know that the x coordinate is cosine and the y coordinate is sine. So, there's some things that you need to know and some things that you don't. From there, let's say to get sine and cosine, you can use Pythagorean identities, but you can also just draw the right-angled triangle. Right, so this is for alpha. You can say that your sine in the second quadrant is positive, so it is 1 over root 10, and your cosine is, the x-coordinate is negative, so it's negative 3 over root 10. For beta, this is the angle we're looking at. Third quadrant, both sine and cosine are negative, so we just read it off and put a negative there. Now, these are the kind of questions that are very much all over the SMO senior. They're not difficult. They are sort of like a question that you would get in your school exam too. However, in your school exam, if you make one small mistake, maybe you'll get 3 out of 4 or 4 out of 5, right? That doesn't happen here. And you can be assured that the multiple choice options are there to trick you. So be extra careful and don't feel bad to, double check and spend more time on these questions, because it may turn out that most of your marks are going to come on these kinds of questions rather than, let's say, the elegant but difficult questions. So be extra careful. In any case, once you have put this in, you get -3, -3 is 9, and then 1 and -2, so you get 7 over root 130, and so answer to question 1 is D. Oh yeah, by the way, if any of you had any issue keying into the answering form and you said, oh, I put the answer but it's wrong, please tell me. I know that sometimes when I enter in the form, it's possible to have some typos, right? I'm quite sure they're correct, but please do let me know if anything doesn't square between what I'm saying here and the answering form. Okay, so question 1 is D. Question 2. Now here is a 2-in-1 question. It's a 2-in-1 question because you need to know your log identities and you also need to know your Vieta's formulas. Right now, Vieta's tells you that the sum of roots would be minus -20 over 1. And the product of roots would be 25 over 1. So that's statement 1. You need to know Vieta's. This is from SMO Junior. You need it for quadratics already. You still need it for senior. Then you have got to see how to get from here to the logarithmic expression log AB plus log BA, which is not very difficult either. It's just that you need to know that by the change of base, you can write it as just log base 10, your common log of A and B, and then rearrange it to look like your symmetric expressions, which may be obtained from there. So you get log A plus log B squared minus 2 log A log B over log A log B, and then just substitute in the values. Okay, so this is option B. For question 3, now this is relying on our understanding of surd/indices expressions. There are certainly ways that you can compare these 2 by 2. There are also certainly ways in which you could kind of intuitively guess the answer. This is actually a good idea sometimes, which is that just see if you can, like if you see a clear pattern, I mean this pattern is very obvious, just imagine extending it in both directions to extreme values. Let's say if you were to go up 1 step, this would just be 1. And so clearly 1 is smaller, and so we have reason to think that it's actually getting bigger. And if you extend it to the 9th root of, like, let's say 9 nines, this is going to be very close to 10. So we can roughly say that in fact the numbers are increasing, and probably the answer is E. Now this is of course just we hope. But just looking at how question 3 went, of course many of you would get it right. So if you got it right by doing a lot of work, realize that it could be guessed. Let me show you the nice method, however, which is also more rigorous, which is that since the number of digits is actually like, square root of 2 2s, 3 3s, cube root, 4 4s, 4th root, and so on, I can actually divide all of them by 10 and so on, which is very close to each of these. If we do that, actually, it is pretty obvious what is the correct answer, because when you take these are all less than 1. When you take something less than 1, the thing actually increases as n decreases. So which means that because it's less than 1, these exponents, you get the smallest exponent, which is good, and you get the largest base, which is also good. So you have the largest base and the smallest exponent. That gives you the largest thing when all of these bases are still less than 1. So that's the reason why we can be sure that option E is correct without having to do any side-by-side comparisons. Of course, you could estimate each of these to the nearest integer because that's not too hard. However, I think this is certainly a bit faster. Okay. Number 4, and we are back again to our trig identities. Observe that when you are handling your trig identities, don't just look at whether they are sine, cosine, and tangent. Look at how many different angles are involved, right? For question 1, there were 2 different angles. And the information was kind of given separately. So you will just handle them one at a time. Now, as far as is possible, if we just can handle it one at a time, nothing can be too hard because we have so many identities linking sine, cosine, tangent, as well as the multiple angles of whatever sine, cosine, tangent you're using. So it is never going to be too bad. Okay, now for this one here, how are we going to do this? Well, I will start by saying that I can convert everything into sines and cosines because that is usually a better thing. And there are 2 reasonable options here. One is to square it first, and one is to handle the inside and then square it later. I'll tell you that both of those are fine. I will just simplify the inside first because I can tell it is related to the double angle. And also because technically I could ignore the square. I mean, if you ask me to square it, I could just find the inside first and then square it later. So I don't have to square it immediately. The squaring is going to just give you a bunch of like numbers that look bigger in your fractions, but it's still going to be enough to worry about the inside. However, if you square it first, it is fine. Now I can see that this is cos 2a, and this is actually 1/2 sine 2a, which means that this is actually 2 cotangent squared 2a. Sorry, no, 2 cotangent 2a squared. Now I said convert everything to sines and cosines. Why am I okay with this? Because that's already 2a, right? Cos 90 minus 2a. Remember that co stands for complementary in all your trig identities and functions. So cosine is sine of the complementary angle. Cotangent is tangent of the complementary angle. Cosecant is secant of the complementary angle. So there you get a bunch of identities for free just from knowing where the name comes from. So if I know sine 2a, I have no problem really getting to cotangent. I can just choose to do it however I want. And among the many choices, what I can do is just to say that actually it's just cosecant squared minus 1. This is one of the identities, but you can also go and just find your cosine and tangent, do it however you want. Sine 2a is this. The reason why is to save myself numerical computation time. I'd rather do algebraic stuff, right? Algebraic stuff are faster than, let's say, squaring, square rooting, squaring, square rooting, subtracting, and adding. Because cosecant is just going to be the reciprocal. And so all I have to do is just to substitute, and then there's only one final computation to do. So substitute it in, I will fast forward the computation a little bit. And once you have done it, you will see that option C is the numerical value. When I first gave this paper, some of my students remarked that it was quite difficult. But when I asked them what exactly is difficult about it compared to, let's say, some of the other senior papers, they had a bit of difficulty, like pinpointing what the exact issue was, because, technically these are identities that are familiar, right, for anyone who is preparing for SMO Senior. So I think that this is just my habit, right? I try to make sure that the special values are not too special, like I don't want everything to be just 3, 4, 5 and guessable. So because of the fact that it's not very guessable as some SMO papers, that makes it a bit harder. But it is still going to be the case that all of these identities are useful. Just that if we are fortunate and the SMO gives nicer numbers, then of course you will save a lot of time. It's 3, 4, 5 versus 65, 56 and stuff like that. Now, lastly, question 5. This is the sort of question that I like to give as, if you will, a teaching kind of exercise. It is not that it is a trick question, but rather that I want us to have the correct perspective on this, because it helps with a lot of questions other than this one alone. Now, Px is a polynomial which leaves a remainder of 10 minus 3x when divided by x squared minus 3x plus 2, 4x minus 4 and divided by x squared minus 4x plus 6. Find the remainder when divided by x squared minus 4x plus 3. All of these are very clearly factorizable. I have made no attempt to conceal that at all. Right, so there's x minus 1, x minus 2, x minus 2, x minus 3, and then this one is x minus 1, x minus 3. Now, you can actually just use your remainder theorem, but I want to just give some intuition, which is that effectively, these are like modular arithmetic for polynomials. You can say that based on the information, Px is congruent to 10 minus 3x mod x minus 1. And you can add 3 times of x minus 1 to say that it's 13. Sorry, no, it's not 13, it's 7. And likewise, you can say that Px is congruent to 4x minus 4 mod x minus 3. And if you subtract 4 times of x minus 3, you get 8. And then you can actually just check each of these to see whether they are actually correct, because this is x minus 1, x minus 3. However, what I've just described is actually the essence of the remainder theorem. The remainder theorem tells you that Px divided by x minus a gives you a remainder of P of a. And the reason for that is simply that if you consider mod x minus a, x is congruent to 8, and so you can just replace x by 8. Okay, so this is actually the intuition which you may want to have. Now, certainly if let's say that we applied the remainder theorem, the outcome that you would have is basically going to be that this is P of 1 is equal to 7, and P of 3 is equal to 8. And then you can substitute into these to check which one is correct, and you will see that the correct one is option B. And so this question here, it just gives me the chance, rather than just using the remainder theorem, which is not wrong. it gives me the chance to talk about the fact that your polynomial division and all is actually something that you can state as a modulo arithmetic like statement as well. And that's because modulo is just talking about division and remainder, and as long as you can have division and remainder, you can have mod as well. Okay, so you can try to see if you have any questions on this ask, but you can use the usual remainder theorem approach. I just feel that this is surprisingly interesting to note because it's something I did not realize as a student that the remainder theorem and modular arithmetic were actually the same, right? It's only something that I observed quite a bit later. Okay, and now that we are through with this multiple choice, we can just look at a couple more short questions before ending this first part of our video. And I will start off with question 6. Still more identities, but with constants instead. The next thing you want to understand about your identities is that don't stop at remembering the formulas, which many of you are dutifully doing. Also know when they are nice, meaning that what kinds of things they can handle. When it comes to trig, the thing that they can handle very well are situations where the angles are related nicely, and angles are related nicely meaning that the sum is nice, meaning a special angle, the difference is nice, or something's a multiple of each other, and then you look out for each of those. Now, if you are looking here, obviously the bottom has all the 40 degrees appearing a couple of times. And the top has 25 and 65, which actually sum to 90. So we can make use of those as far as we can. You don't have to make use of everything, but make use of the niceness of it to determine which identities you want to use. Now, for the top part, you can use either your, change sine 65 to cosine 25 and use your R formula, or you can just use the sum to product, which I'll just use the sum to product here. Right, the premise of sum to product is to write the angles as a sum and a difference. That's pretty easy to do, right? Just get the average and then you add and subtract half the distance. These will cancel, and so you get √2 cosine 20 degrees. Okay. Meanwhile, for the bottom, they're all cosine 40 degrees. Which means that in theory, if I want to get cosine 20, I could just use my double angle formula, but I feel like that may be quite ugly if I use 40 to get 20. Since it's an SMO problem, however, you know that it will cancel. So as long as I find a way to simplify, the values must turn out to be nice. And so I actually just grab the 2 cosine squared minus 1, and I'm going to use the double angle in reverse on that. And then for these two, I will then use my sum to product on cosines, where this time it is 60 plus 20, 60 minus 20. So when you see the same angle appear again, that's good news. Indeed, this is 2 cosine 60 cosine 20, which is just cosine 20 degrees. Therefore, S is square root 2, and your answer is 20, rather aptly as well. So you have to know where do your identities excel at, which is that the angles are nice in some way, and also recognize that, let's say, sum to product works on no coefficient. So if it's sine 25 plus 5 sine 65 degrees, I would need to use the R formula by changing sine 65 to cosine 25. So know what your identities can do. Don't just remember the statement. Understand them for what they do and not what just the statement says. Okay. Now, one additional thing. Also understand what your identities cannot do. there are no identities that can deal with this. At least not without making a huge mess. And so it is often forgotten by us Olympiad participants that there are more equations that cannot be solved than can be solved. Just like, if we talk about it, the integers are only an infinitely small proportion of real numbers. And someone who knows small set theory will, of course, be able to phrase that more precisely. But, it's like integers are just very special. So, in fact, there are many more things that are not integers, but in primary school, we just keep on using integer stuff for a lot of things. So likewise, don't always think of those identities. It's only that the SMO has chosen questions where they usually work. But you must acknowledge where they don't work and then ask, okay, then how can I solve the question? For this case, this is a pretty frequently seen trope as well. To just recognize that this is actually increasing. So increasing function x, you don't need to differentiate in order to know that, right? I mean, cube root is going to get bigger and bigger. X has to be positive, but x minus 25, even if it's negative, I know cube root is still an increasing function. So no differentiation required. Square root is obviously increasing as well. And so therefore, for it to be a constant, that means that there's only going to be one solution. And if there's only one solution, you can sort of binary search it with a higher or lower search, knowing that the answer must be integer, and also that the cube root and square root must be integer as well for this to work. So you can sort of try, let's say x is 2025 itself, you will get the left hand side is 45. And then the next time when you have got x minus 2025 is an obvious cube, for it to increase enough, this cube root needs to increase and the square root needs to increase by about 10 each. So it makes sense to take, like, let's say, x minus 2025 to be 10 cubed, which is 1000. And lo and behold, that actually is your answer. Because square root of 3025 is 55 exactly. So not this, so this is the answer. And if this is like sort of like guessing, yeah, it is. But the thing is that being able to guess is not just a skill, but it is also something that you need to discern. When is it that the question conditions make it such that guessing a root is actually intended? Just like that's how we factorize cubics for a human. So know your identities, know what they do, know what situations do you prefer to use them, and also know when your identities don't work, i.e. you need to look for something different. Alright, so this is part 1. In the next part, we will continue looking at the next 6 problems, but feel free to leave any comments below, and feel free to continue trying the rest of the questions until my next video is out. So thanks for watching, and bye for now.